Hello everyone and welcome to a new episode of All Things IDA. In today's episode, we're going to continue with the PE file format exploration. Last time we mapped the file format from scratch all the way into the database. We changed the segments and mapped the sections accordingly. This time we're going to interpret the import directory from the file in the database. So assuming that you followed through from the last time, we can continue by just looking at the data directory and take it from there. So let's get started. All right, so last time we were talking how to load the file manually by hand, and that's what we did. We loaded it. We explained the headers and progression. First the DOS header, then DOS header points with the ELFA new to the NT header. So if we go follow it, we reach here the NT headers. We have the signature, file header, and the optional headers. They are all as a single blob. So if we go here to the NT header, you can see it's composed of the signature, the file header, and the optional header. And here, for example, from the file header, we have number of sections, for example. And from the optional header, which we'll focus on today, it has so many fields. For example, address of entry point and other stuff, but in particular, data directories. And it has 16 data directories. Here we have all those data directories. If we go to the documentation online, in the optional header, we have data directories. In the data directories, by convention, the order they are laid down dictates their role. So the entry number 0 is export table and entry number 1 is import table. So today our first thing we need to do is the import table. We want to interpret the import table. So let's go back to the structure here and fix it. So what we're gonna do, instead of having the optional headers be 16 as in the 16 of array, let's just break it into individual elements, and then we're gonna rename them accordingly. So the first one, just gonna call it export directory, and the second one that we care about is the import directory. So we're gonna call this import directory. Now let's go and see, and the rest are dummy for now. We don't need them, but just like, for example, the one before the last is CLR runtime, I could rename it, and this one is reserved and so on. So let's take a look first here what we have. So this is the NT header, let's expand it. And now the directories are individual. So here we have export directory with its members. So it has 0 virtual address and 0 size. So that means we don't have any exports in that module. Now here we have import directory, and it does have information. Same for the other fields, which we're not gonna look at today. So for the directory that designates the import information, it's an RVA. Same for all the other fields in the data directory. So a data directory is made of two fields, a virtual address and a size. The virtual address is relative to the base. So here the real import information is really that number plus the image base. So if we go to the top and jump here, this is really the import directory virtual address. That's what we need to interpret. And starting from here, it does have a specific structure that we're gonna explore. So one quick tip is, let's change the way those RVAs look like. So we don't want to see RVAs. So all those virtual addresses are really not full addresses. Therefore, I can't immediately make sense out of them. So let's fix that real quick. So this field here, like all the other virtual addresses fields, belong to the data directory structure. So let's go to image data directory, go to that field, and change the operand representation offset, user-defined offset 64. And that's the base. This is just a way to tell IDA how to render that address. And it has a pre-built set of representations and calculations. And here we're just simply saying it's an offset 64 in function of the base. And so what will that do is simply take the original number that we had and change the expression to be the original RVA plus the base. It will put the full value, and then it will also then do minus base. So the whole expression here really equates to the original value, the RVA. But now what we see in the display is we expose the final target. So that's the actual image import descriptor for that entry. So if we follow an import table from the data directory, which is generic structure, where do we go from there? Depending. So every data directory will have a different format when we follow it. So all data directories have the same data directory structure, but then once we go there, we will see the difference. So for example, for the import table, it will take us to something that describes an import directory table. And the name of that, we're gonna talk about it. So let's switch back to Orange's diagrams real quick, just to show you here what we're dealing with. So DOS header, and then from the DOS header, eventually we'll go to the PE header, the whole thing. We will have a file header, as we said, and we have the optional header. Optional header will have a bunch of directories. And the first directory is the export, the second one is the import, and if we follow it, that's basically what we're dealing with respect to the import. So when it comes to the import, the directory itself will point to image import descriptor. And from the image import descriptor as well, there are a bunch of pointers that we will learn how to interpret. So let's take a look here at the NT header again. So we have image NT header, we have the optional headers, and we have 16 data directories. And each data directory will take us to the appropriate structure. So now the next one here, what we need is image import descriptor. So let's find it, image import descriptor. So the image import descriptor is what we are gonna be applying next in IDA. So the image import descriptor has import lookup table, timestamp, forwarder chain, name of the DLL, and import address table. So what is important here really is we have the name of that DLL we can resolve, import lookup table. Now here this is important, mentions you will see something like characteristics, but it no longer describes this field. So like this is an outdated field, and here this is what they're talking about. And the image import descriptor, this is basically what we were looking at in the table. And so here they're saying characteristics, you can ignore it, it doesn't make sense anymore. So really we have original first thunk, we'll talk about this, and first thunk, and the name of the DLL. So let's bring in the image import descriptor into the database. So open the structures window, add, and then just import the standard structure. And so here, image import descriptor, and we have it. Now the image import descriptor should map what we see here, basically. So the first field is a union, and we can see it in IDA. It's a union pointing to the characteristics or the original first thunk. So this is really not applicable anymore. Let's just get rid of that and get rid of the union and just make it original first thunk, timestamp, forwarder chain, name, and first thunk. Now let's see how we can simply apply this and interpret them. And by the way, if we look at it again here, so when we follow the import directory and it takes us to an image import descriptor, we will get an array of image import descriptor. So once we apply this to the first entry, as we do in a second, so here these are the directories first, and now let's follow the directory to the descriptor, and we'll have an array of descriptors. So here is gonna be first import descriptor. That's gonna be the first import descriptor here. So Alt Q, and let's apply the descriptor here. That's what we want. And apply it. So that's the first descriptor really. That describes one imported entry. If we make array, just press star. Now the array size here is too big really. We don't know how much, but what we need is an empty structure. So we can start by 2 or 3 and see if we need more. So here we still have entries. Let's make it, let's say 10. And already here we have here, this is the empty structure. So that's it. We don't really have 10. We have maybe 4 or something. So, but that's it. These are really the entries. And so what we're looking at here, a bunch of those, which basically will tell us what is the DLL name we're importing from and where are the actual APIs and their names. So let's see how we can interpret the descriptor now. So going back to IDA, the original first thunk, we're gonna talk about it in a second. Let's target the easy ones first. So so those are similar. First thunk and original first thunk are similar. Date, timestamp, forwarder, and the name. The name, it says as well, is an RVA. So the address is just simply an RVA to his ASCII string. So since this is an RVA, here is the name. Same story, right? So we can go back here, go to the top and jump to that. And we have the name. If we make string, we have user 32. So that's easy. Since the name is an RVA, we can also change the representation. Control R, 64-bit. This is the base. Press OK. Now it's marked. So the display now will change. It will show us the name in the form of an expression. So we can follow them one by one here. And since those RVAs are exposed, we can see here. So this is an empty entry. Let's minimize the array by 4 elements. And so we have winmm, ADV API, user 32, and kernel 32. So this is for the name field, which is a simple RVA. So those header, PE header, then directories, and import directories, and the first import descriptor. And from the import descriptor, we can access the name RVA and we print the first name. Now, how can we go to the actual APIs that are imported by those stuff? So that's where we can now start add some lines. Okay, so this is the name. It's super easy. Now let's take a look at the original thunk and the first thunk. They're essentially the same, except that by design, the original thunk here does not change when we run, and the first thunk, it will change the actual thunk data when it's running or when the image is bound. And that will be clear in a second. So what does that mean? So the original thunk will take us to what is dubbed as thunk data. And this is just a number. Either it's a 64-bit number, so really it's just a D word or a Q word. And depending on that Q word or D word, we will basically know what we're dealing with. Are we dealing with an import by name or an import by ordinal? So let me show you and things will be clear. The thunks, either first thunk or the original first thunk, they will point to an array of thunk data, which is 64-bit in our case. Those 64-bit numbers, basically here, so either the original or the first thunk will point to the thunk data. Thunk data is gonna be either 32-bit number or 64-bit number. Now that number is encoding 2 bits of information. If it's an ordinal or it's by name. And so when we read the first pointer pointed by the RVA, if the high bit is set, we know we should not follow it further. If the high bit is not set, we interpret that as another RVA and we follow it to another structure that is import by name. I know it's not clear unless I show you by example. So let's take a look here. So original first thunk is gonna point to an array of thunk data. And this is an RVA. So let's just fix it first to make it expose the full address, which is image base plus this number. So going back here, original first thunk, let's just make sure it's correct. And since this is gonna be the same, it's an RVA to thunk data. That's good enough. And now going back here to the original first thunk and follow it. We're just gonna make a Q word, Alt D and Alt Q. And that's a Q word. This is the first thunk data. We can safely make an array until we encounter 0. So here I automatically detected 78 array elements. So this one here, let's see, this is the DLL called kernel 32. So let's call this image import descriptor for kernel 32. And this one is the original first thunk for, that's the beginning of the original first thunk of kernel 32. So let's call this original first thunk kernel 32 as well. And these are the arrays. Now those arrays should either be designating import by name or import by ordinal. Looking at those keywords, they definitely don't follow this. They do not have the high bit set. If they had, then they're importing by ordinal. But since they're not setting the high bit on, we can treat this thunk data as another RVA to import by name structure. So here, if we go back to the imports and add the structure called image import by name, we should basically see it's really a variable size structure that has a hint and just the beginning of the name. We'll see what that means. So this original first thunk, it seems all of the members are not by ordinal, so they are RVAs. So let's just make Control R and expose the full address. So this is the first address of the actual thunk data pointing to import by name. So here the lookup, it's gonna be either by ordinal or by name. And now that we follow the first thunk to an import by name, let's apply an import by name at the destination. So here, this is the import by name. It's not gonna be very descriptive. I'm not gonna use it because it's a variable size. The import by name really captures basically the hint and the name. So what is an import by name? Importing by name, and we can see it even in the MSDN. So let's follow it here. When we import by name, we may specify hints and the name of the API. So really, if we're gonna do it by hand, we follow one thunk data, let's follow the second one, let's say, we follow it. We expect an import by name, which means we have a D-word hint and a variable size name. So here we follow it, DD, this is the hint, and a 0 terminated string. This is the imported one. And so here, Control R, let's just make Control R on all of those. And thunk data, each thunk data will point to an element. Close handle. Second one is after the hint heap realloc. Third one after the hint is heap size. Now you may be wondering, so we are at the import descriptor, we follow the origin first thunk, and we know the thunk data, and then basically we know the import by names. But what about the actual pointers? Where are they resolved and how the program uses them? So here we know, for example, the thunk data pointing to import by names, but where are the cross references to those APIs? Let's take a look at the first thunk. So if I go now to the first thunk, it's gonna be the same, an array of thunk data here, another array. Let's make a DQ, make an array, and as well IDA detected 0. This table, it's identical in explanation and structure, but it's another table. But the role is the same, but different at runtime. We'll explain about that. So now, here, original first thunk, you see it's a different table, but containing thunk data pointing to import by name. So what I'm gonna do, going back to the origin first thunk, I'm gonna just give some names. So origin first thunk here, let's call this one K32 import by name, number 1. This one, import by name number 2. So these are the original first thunk array. Let's take a look at the first thunk array. It's gonna point to pointers. First, let's make them as offsets. So, and then break it as an array. And look what you have now. We have that first thunk, the array of the first thunk data, are still pointing to the same import by name structures, but they're completely different locations. So we have two arrays, two thunk data arrays. One pointed at from the original thunk, and one is from the first thunk. The original will point to the thunk data that will lead to image by name, and the first thunk will also lead to another array pointing to image by name, but the difference is when the process is executed, operating system does the resolution, every time it resolves a thunk data entry from first thunk will be replaced by the actual API pointer. And that's why every thunk data pointer is pointer size. So what does that mean? I'll show you what that means. Let's run this process side by side and see what happens. So let's run it with the actual one that is fully loaded and so on by IDA. What I want to show you is the import resolution. What will happen when we actually run it? If we inspect the same binary but in the memory view, if we go here, this is taking us to the image import descriptor of kernel 32. And then we have the origin first thunk will have thunk data pointers pointing to either ordinal or image by name. So let's follow the same here. This will be all the original first thunks. These are individual thunk data elements, either pointing or they are ordinals. So let's follow them. And here we have thunk data. The first bit is not set, therefore it's an RVA. Because it's an RVA, we can follow it. It will still take us to import by name. And we have the same import by name. The difference now is we run it. Now we have import resolution, or what we call binding. So now the first thunk will point to thunk data, but those thunk data no longer points to import by name. Instead, they're bound. So those pointers will be resolved. So here on disk, first thunk just takes us to thunk data array. That array is not bound yet, so it still points to image by name. Now we run it. So we run the process. It's bound. The whole first thunk now, all of those first thunk pointers are resolved. So here, this one was pointing to by name to close handle. It should be replaced. The whole pointer now should be replaced by. So let's follow the first thunk here in that descriptor. So we're gonna go to 74 here, the same one, and follow it. So this one really is the kernel 32 first thunk array. And here we have that used to be import by name resolution. And now look at this, it's actually resolved fully. So let's randomly pick another DLL. So here, import descriptor array. Let's pick, let's say, the last descriptor, expand it. Same story, origin first thunk will point to thunk data array. So let's follow it. Here we have an array. Let's make it and let's follow it. So origin first thunk data array, thunk data array. Either high bit is set, we don't follow it. High bit is not set, we follow it to import by name. So this one, the first import by name, points to a hint. This is the hint, so the hint should be 2 bytes. And then the name of the API. Same story here, hint and name of the API. Hint and name, and so on. And we could have done the same here. So if I follow this one here, let's call this WinMM import by name entry 1. So here we go, this one. And for the first thunk, same story. It's gonna be the same IBN. But the difference is the first thunk, all of those IBN pointers will no longer be IBN. In fact, they'll be part of the whole import table. So if we actually look everywhere, these happen to be the first thunk values of different DLLs, and they are consecutive. And then that's what we see manifesting in a single segment here. We see a single segment with all those pointers resolved, just because the first thunk points to the thunk data to pointers that are consecutive, and we see them like this. So what we're gonna do is just write a small script and ignore the original first thunk, follow and interpret just the first thunk. We're gonna display the DLL name, and then if an import is import by name, we'll follow and display the hint and the name. If it happens to be an ordinal, we're gonna display the ordinal and we're not gonna follow it. So let's see if we can basically statically from our database display that kind of information, the DLL name and where is the API is going to be resolved and which DLL. So to some degree, have the same view as the imports, basically the DLL, the API, and where it will be resolved at. We have all this information from this bit. So let's write a small script for that. Okay, so let's write some code and hopefully this will make your understanding much more solid. So here as well, I'm just gonna use snippet window, and we're gonna assume we parsed everything and even the data directory, and we're starting from the first import descriptor. So here, let's say image import descriptor EA is this one. Okay, so now, as we've seen from previous videos, I want to grab that piece of information and interpret it real quick. So the first thing is, I'm going to use structured data retrieval, and we're going to use app call mechanisms. So here, take the structure name that I want to deserialize and say image import descriptor type equals typed object. So I created a typed object. Now the second thing is, let's retrieve that. So here, let's say while true. Okay, and objects, I can just say IID as well, which is the object I'm retrieving. IID typed object retrieve at IIDEA. And if not, okay, or IID dot, basically what we want to check is the name RVA is none. Name is 0, let's break. Otherwise, just make sure we have IIDEA increased by dot size. So let's advance. Since this is an import descriptor array, let's advance by size. Otherwise, let's also hard code for now the base. So let's also capture the base and display it. Okay. So now we can say print, for example. We can first display the IID, the image import descriptor. So let's say descriptor at IIDEA, and name RVA for now, and we're gonna resolve the full name in a second. Let's try this out. So first here, let me clear the screen, run it. Okay, so we have the first descriptor here, name at 714. Yep, okay. So now the second thing, I'm gonna say IDC dot get strlit contents, and we're gonna compute that as well. So here, let's just take the name, and the name is convert the RVA to VA. So here plus base. Okay, I don't need the name RVA anymore, so we can say name is name. Let's see how that works. So here we go. We got the names of the DLLs. Now it shows the B. We can get rid of the B with a simple decode as UTF-8. Let's clear the screen and run it. Okay, so we got just the name from the import descriptor. So now let's take the first thunk and walk it to get the thunk data, which is just pointers, and determine if they're gonna be import by ordinal or by name. So let's get this guy, first thunk. So we need to do another loop, dot this guy. And as we said, we're gonna interpret every thunk data So let's see, thunk data is ida API dot get keyword of this one here, and this one here, although the thunk data is going to be import by name or not, this IAT is no longer going to be pointing to image by name. It's going to be the actual final result. So let's increase it at the end, but we're going to use it in the output. So here, this is the resolution address. So I'm going to just put it like this, as if it's dereference. And that's where we're going to be resolving the APIs we're going to be outputting. So these are all our resolutions. Now our breakpoint here is if TD, we are done with the array, no more thunk data member. And because of that, we can no longer follow anything. And once we don't follow, we don't have an ordinal or we don't have a by name. So we're done. So here. So this is the thunk data. Now we're dereferencing from the first descriptor, first thunk, and a bunch of 64-bit values. Those 64-bit values will either be final pointer when we run it, or right now as we interpret it, it's going to be the information about the DLL. So right now, just let's display IATs. So that's problematic. Let's fix the problem. So yep, real quick, the problem was I forgot to put the base, of course. And so because I don't have the base, I was reading incorrect values and causing the whole of the problems. So let's try it out again and see. So we have here, for example, kernel 32. This is one entry, second entry, and so on and so on. And it seems to have all the stop conditions are correct. So it detected as many import descriptors. So these are the parent DLLs and those stuff. So now let's try to see if the thunk data is by ordinal or by name. So if this, let's say, and since we're working with 64 bits, so we're gonna check this. Okay, maybe we can do it like that here, ordinal. We're just gonna say, in this case, is enough for us really to just end it with, since ordinals are even not that long, to be honest. All right. I don't think we have any import by ordinal, so it's not gonna be useful in that case. But if it was by ordinal, then not by ordinal, then we're gonna say image import by name. So let's say IBN import by name EA is, we're not gonna do the same mistake again. Add the base, that's good. And so here, let's say, just for now, just to test it, IBN EA. Let's see. So all those are IBNs. So this is where it will resolve to, and this is how we actually got the information. So what we need is get info CP, and so on and so on. And so what that means really is, if we take this IBN describing this here, get process heap, this tells us that if we run that program, get process heap will be resolved at IATEA. What's IATEA? It's just an index of the first thunk designation. So if we look at here and go to that, so let's pick something. So let's pick this one. This one is get OEM CP. If we go here to the same address, here we have get OEM CP. In fact, we can rename what we're doing as well. So here we can rename all those entries which are thunk data to actual import names. We can rename them at the end. So now let's supplement this with just the retrieval or interpretation of IB image import by name. It doesn't make sense to use typed objects for this one since we're dealing with variable size structure. So here the name is gonna be more than one character. So retrieval is not really gonna save us time. So we're gonna do it by hand. So here the hint is ida api.getWord image by IBNs, and the name of the EA of the API, we can also do the same. So we're gonna say it is get that dereference at IBN EA plus base, which already is there. So all we have to do is just simply skip the hint, which is 2 bytes. And we don't really need to display the IBN anymore, just the name here and the hint. Let's see if that will work. So let's save it and run it and take a look. So because we are walking the first thunk, that's gonna be the final import address of that element. And so let's pick something at random. Let's say find close. In the resolved version here is find close. Let's follow it somewhere. And since our database is not analyzed, we have analysis off. So let's go here and make code. And here, you see, if I let the analysis finish or start even, it will pick stuff up. It will find calls to somewhere, but that somewhere, now we actually know where that somewhere would be and what that name would be. So what I'm going to do as a last step is simply rename those pointers. So instead of having just display here to print them, we're gonna rename them accordingly. So just gonna do that here. So find close and so on. So we're gonna use the ida api.setName API, and we're gonna just give it the name and the address and so on. So here let's say ida api.setName. Where are we renaming? We're renaming all the IAT pointers. Okay, let's try this out. Remember, we can always undo, so there's no issue here at all. Right, so let's try. And look at this. We have all those nicely renamed. Now, I didn't make a keyword. Okay, so what we need is create a keyword at that location as well. So let's try this one. So yeah. Okay, I have all of them nicely created as keywords. Okay, I think we uncovered a lot of information. Let's try to see what we can get out of analysis. So let's see. So now, because I renamed the imports, although they are not processed by an IDA file loader, they still have some meaning. Meaning, because of their names, because of the type information library, we get the prototypes, then the call analysis will do a better job annotating the call sites and so on and so on. Now, what we don't have is imports here. This is something populated at actual loader time. We don't have it right now. We're doing everything by hand. So here, this is really an import, or we have to do tell IDA that that's an import. But for the purpose of our video, we now know how to populate this by hand. Maybe last thing before I finish, I'll do the same, but just printing out and starting from the original first thunk. And it's gonna be a different story. So here, it's gonna be the IATs are not gonna be what the actual program refers to. So let's take the original first thunk as our enumeration field. Instead of first thunk, original first thunk, everything remains the same. No need to rename here. And do not create keywords, because the original first thunk is not gonna be changed. The addresses will still be pointing to import by name. And so that's why it's called original. It's not gonna change the value. It's not gonna bind. So let's run this. The only difference is, instead of working the first thunk field of the import descriptor, we're working the original. As per the documentation we said, they are the same, except at the bounding time. That's the most important part. All right, so let's try this one here. Same story, but notice close handle, we think if we walk the original first thunk, it will resolve to 3F0, but in reality, close handle is really resolved at the first thunk says thunk data. So that's the resolution, not that. That still remains the import by name thunk data. So these are all the thunk data array, but they are import by name, not changed during runtime. They're not bound yet. So that's it for today. We covered how to go over the imports by hand and worked through the difference between original first thunk and the first thunk and thunk data and so on. We built a script. We also showed you how to use typed object parsing as well to make sense of that data. So for next episodes, we will cover the export directory and take it from there. Thank you and see you next time.